Hi, my name is Eric Bogatin. I'm a signal integrity evangelist with Teledyne LeCroy. In this brief video, we're going to take a look at some of the important features in the deep toolbox of the WavePulsar 40iX that enable us to get a quick view of how our channel is going to perform in a system. One of the important innovations introduced in the WavePulsar 40iX is this idea of having three different measurement and analysis modes integrated into one instrument with one user interface. In previous videos, we've looked at some of the features in the 40iX that allow us to get to quality S-parameter measurements quickly. When there are 4 ports involved, we can look at the S-parameters as single-ended S-parameters and as mixed-mode S-parameters. As you can imagine, there's a lot of data to manage. And that's why the built-in features for the display of the data gets us to the format that gets us the most useful information as quickly as possible. In addition to looking at the data in the frequency domain as S parameters, we can also look at the response of the channel to time domain waveforms. And that's the regime of TDR or TDT measurements. And with the 4 ports, we can look at the TDR or TDT response either as single-ended or as mixed mode. Whenever we care about spatial information of the interconnect, that is, where are discontinuities located, where does coupling occur, where does mode conversion occur, we always want to be thinking about displaying the data in the time domain and looking at TDR response. The integration of these two features means that we can quickly and easily go back and forth between looking at the frequency domain response of our channel or the time domain response of the channel, depending on the kind of information that we're looking for. In addition, the deep toolbox capabilities of the WavePulsar 40iX allow us to take that measured data and analyze it quickly. In the last video, we looked at how we can use some of the software features built into the toolbox in order to take the S-parameter data and either de-embed fixture effects with 2 mouse clicks or renormalize the ports so we can look at the behavior of our channel, how it would behave in a different impedance environment. For example, a 75 ohm impedance environment. In this video, we're going to look at using the measured S parameters as a behavioral model and looking at how we can use that in order to quickly emulate how would a signal behave if it were coming through that particular channel. This is not really a substitute for a good system-level simulator that might include the driver models for the transmitter and the receiver and other circuit elements that we could vary in real time, but it will give us a quick view of what we would expect to see in the channel based on the S-parameter performance. So let's take a look at how we're going to do that. Using some of the features in the WavePulsar 40iX Deep Toolbox, here's what we're going to be looking at. First, of course, we always want to take a look at the S parameters that we've measured. This is always the starting place. And if we understand the features of the S parameters, we can do a quick analysis of what we expect to see. This is rule number 9. Anticipate before you do the simulation or the measurement. So by evaluating the S parameters, we'll have an idea roughly of what to expect to see, and then we can synthesize a PRBS signal. We can create an emulated scope, so we have an idea of what a scope would measure if we were looking at the signal going into the channel or coming out of the channel, what a receiver would see. And then once we have that signal at the receiver, now we can manipulate it. We can look at an eye diagram based on the received signal. We can recover the embedded clock using clock data recovery techniques. We can stress the signal a little bit, change the data rate, add noise, add jitter to it, look to see the impact given the channel performance on that resulting eye, and we can analyze the eye a little bit and extract a few useful parameters for it and even change equalization. I'm going to walk you through one simple example that will highlight some of these features. Let's get started. To emulate the behavior of a channel as represented by the S parameters of that channel, we can literally take the measurements we've just completed, or we can import a touchstone file that contains those S parameters. So in this case, we're going to grab a touchstone file of measurements we've taken on a particular channel. The differential return loss starts at a large negative dB, exactly what I expect, and the differential insertion loss starts at 0 dB, drops down pretty darn monotonically. that's what I expect to see. So it's a well-behaved channel. Now we can look at the values. We're going to expect to see if we have minus 10 dB of attenuation at that frequency, at that Nyquist, that is going to be the highest data rate we can send through and still see an eye that may be open enough. So that corresponds to about, here is 4 gigahertz. So minus 10 dB is about 5 gigahertz Nyquist. That's 10 gigabits per second. I would expect that maybe I could get a 10 gigabit per second signal through this channel, but not much more than that without using equalization. So to start out, just to see something that's useful and to look at some of the features in the eye, we're going to use an 8 gigabit per second data rate. We're going to send a NRZ PRBS signal at 8 gigabits per second through this channel. We'd expect the eye to be relatively close but open enough in order to be able to use it and see some of its important features. So we're going to synthesize PRBS signal at 8 gigabits per second. We're going to emulate one of our WaveMaster scopes, which will be taking data at about 80 gigasamples a second. We'll look at the signal going in. We'll look at the signal coming out of this channel as described by the S parameters as a behavioral model. We'll look at the eye that's generated, and then we'll change things up. We'll change some features in the signal, we'll stress it a little bit, see the impact on the eye. So let's get started. And to do that, we're going to take advantage of 3 built-in tools in the WavePulsar 40iX Deep Toolbox. They can be found under the SI Studio menu. The first one is the signal generator. That's where we're going to synthesize the PRBS signal and emulate our scope. The second one is the channel emulator, or our eye doctor, and that's where we're going to include the S parameter behavioral model, send that signal through it, maybe add equalization if we want, look at the signal coming out of the channel, that distorted PRBS signal, and then we're going to use our serial data analyzer in order to take that distorted PRBS signal, recover the clock, use a slicer to slice it up into individual bits, generate an eye, and do our jitter analysis on that eye. So let's first get started with the signal generator. We open up a new window down here to generate the signal, and we have 4 different simulators we can use. We're just going to use one of the simulators. We're going to set up our scope emulator so we can actually see that signal that we generate. Here's where we set up our scope emulator. We're going to emulate our WaveMaster scope, which can acquire data at 80 gigasamples a second. So we're going to make this 80 gigasamples a second. We're going to take 400,000 samples, 400K samples. That's going to be our record size, or our buffer size. And if we have 400,000 samples and it's sampled at 80 gigasamples a second, the time for that buffer to be acquired is the 400,000 samples divided by 80 gigasamples a second. That's 400 over 80, that's 5. That's going to be kilo over giga, that's minus 6, so it's 5 microseconds is the buffer size. So when we take data, we're going to take buffers of 5 microseconds. We're going to view the signal going in, the signal coming out. We're going to slice it into individual unit intervals and look at the eye, each buffer acquisition. We set it up over on the right hand side. We're going to select an NRZ signal. We're going to use our 8 gigabits per second as the data rate. Now, normally, the rise time for 8 gigabits per second, the unit interval is about 125 picoseconds, and the rise time would be something in the order of about 20-25 picoseconds. So we'll use a rise time of 20 picoseconds in this case. Obviously, we can vary it. We can stress the signal in various ways. We'll keep all of the stresses off for now. So for example, we can add vertical noise. We can add asymmetries between the P and the N signals. We can also add jitter, but we'll keep all of those off, both the random jitter and any periodic jitter, just so we can see that signal initially. And now that we've got our scope emulator set up, we can actually see some of that signal. So let's turn on, and we'll just look at the P signal. Of course, the M is going to be identical, just opposite phase. And here it is. It is a minus 2.5 to plus 2.5 microseconds, our 5 microsecond window of acquired data. But of course, with a unit interval of 125 picoseconds, gosh, we can't see the individual bits here. So let's zoom in, and now we can see here is a 1 bit, a bunch of 0 bits, a bunch of 1 bits. And this data pattern is just that zoomed in a little bit in the very center of this large data pattern in our 5 microsecond window. So we've got our signal going in. Now we can send that signal through this channel, and that's where we're going to use our channel emulator. So again, under SI Studio, we pull down our channel emulator. This is really our iDoctor 2 tool. This is going to allow us to bring in and select where do we want the input signal to be. We can add a little bit of pre or de-emphasis to that signal if we want to. We're going to keep it off for now. And then we can select what channel do we want to bring in as defined by the S-parameter behavioral model. And if we want, we can add some equalization, which we'll keep off for now, but we can turn on later. Well, the input signal is going to come from the differential signal of our synthesized PRBS signal. So that's going to be our simulator channel 1, the P signal, and the other input 2, is going to be channel 1 of the M signal. And so we have the option of choosing a variety of different signals. We can even take measured data if we have it and bring the measured data in and use that as the synthesized source. So we've got the synthesized PRBS signal coming in as our source. We don't really have to define the data rate here because we're going to use our clock data recovery software feature in order to measure that embedded clock for each acquired buffer. The next step is the opportunity to add emphasis, pre or de-emphasis. In this case, we're going to keep it off, but we could add a little bit of pre-emphasis or de-emphasis if we choose to. Of course, this is a pretty long channel. This is 20 inches long. That means we're not going to have a lot of signal coming out, and so we would probably want to use pre-emphasis in order to pop the eye open a little bit. And that's something that we can do in a later exercise. The last step then is to bring our channel in, and we're going to emulate it. So we're going to enable the channel. We have the opportunity of de-embedding a fixture right at the time we bring the channel in, but I've already done that in the measurement. And so we're going to bring that channel in that already has the fixtures de-embedded. And the last step is coming out through the equalizer. For now, we're going to turn the equalizer off. So CTLE, FFE, and the DFE we're going to turn off. Our signal coming out of the iDoctor is going to be the signal as it would appear coming out of this channel. Let's take a look at some of those signals. Well, we can look at the signal going into the channel. That's the signal input. Let's turn it on, and here it is. Now, we don't need the zoom anymore, so I'm going to turn the zoom off. So here's that signal that's going into the rest of our system, and this is after it's been converted to differential signal. But now we can look at what's it going to be coming out of our channel. We're going to expect to see a similar kind of PRBS signal, but distorted. And here it is. Just so we can see it a little bit more clearly, I'm going to go back to single shot, and now you can see multiple ones in sequence gives us more time to go to a higher level. When we have a single bit, we don't get to as high a level. And that, of course, is what's going to give us some of the closure in the eye and contribute to deterministic jitter. Now that we have the signal coming out of the channel, it's also going to be the same signal coming out of the equalizer because, of course, we're not adding any equalization. And so here's that signal coming out of the equalizer. Now we're ready to take that signal and look at what an eye would be. So we can send it through clock data recovery circuitry and slicer and recover that eye. And that's what we do with our third tool, Serial Data Analyzer. So we're going to turn on the Serial Data Analyzer. We're going to take as our input the iDoctor output. That's our differential signal coming out. We're going to rely on finding the data rate every cycle. So that's where it's not important to type in any value. We're going to take that data coming in, and we're going to use clock data recovery software in order to find what the underlying clock is embedded in that data rate. And now we're ready to put it through a slicer and look at the resulting eye. So we're going to turn on the eye, and now we've got our synthesized PRBS signal going through our channel, distorted. We go through the clock data recovery, and we look at the recovered eye. And now that we've got the eye, you can see it's open, and in fact we're able to measure some of the eye parameters directly. The unit interval, here's 0, and here is the 125 picoseconds roughly. This is the unit interval for 8 gigabits per second. In our eye that's with a clean signal going in, we have a width of about 83 picoseconds. That's the opening, and we have a closing about 50 picoseconds. That's our 120 picosecond unit interval. Let's go back to our signal, and let's add a little bit of stress to it. And the stress that we're going to add in this case is a little bit of jitter. We're going to add a little bit of random jitter. And so we're going to turn on the broadband jitter, and we're going to add just 1 picosecond of random jitter. That's the standard deviation of random jitter. And we're going to turn on some of our periodic jitter as well. And immediately you see, as we turned on the random jitter, you can see, wow, in the histogram, we're starting to see a distribution that looks kind of Gaussian. And you can see the crossovers have increased as well. Now let's turn on the periodic jitter. Let's make that 300 megahertz so we can see it. And we'll use a 10 picosecond peak-to-peak jitter noise. And of course, 10 picosecond peak-to-peak is going to be an amplitude of 5 picoseconds. And sure enough, wow, here is our jitter spectrum. Let's turn on the peaks so we can read what that peak value is. We're going to show the peaks. Here's our jitter spectrum. Sure enough, at 300 megahertz, we have this strong periodic peak. And look at that. Darned if it isn't really close to 5 picosecond amplitude, just about what we expected to see. And we see that the histogram has become distorted. We have that bimodal distribution, exactly what we would expect to see. We see our eye has increased as well. And we see that we've gotten a compression in the opening of the eye. Our crossovers have increased. And now we can also, using this distribution, we can fit a Gaussian distribution, a normal distribution, to the tails and see if we can recover that 1 picosecond RMS jitter. So let's do the analysis of that jitter histogram, and we're going to show that Q-fit. And so here is along the tails of that jitter distribution, we're going to be fitting a normal distribution, and sure enough, our fit is about 1 picosecond. And so we're able to recover not only the periodic jitter, but also the random jitter. And this is using exactly the same software tools that are built into our scopes. So in this video, we've illustrated how we can take the S parameter measurements from the wave pulsar 40IX, use them as a behavioral model, and get a quick look at how our system might behave for PRBS signals and what the quality of the eye might be.